morning, dear friends. In the previous class, we discussed about the exact methods of solution, and we also entered into the approximate methods of solution. Why one has to prefer the approximate method of solution? For example, in structural mechanics problem, the complexity increases due to loading, geometry and boundary conditions. When the complexity increases in loading, geometry and boundary conditions, any one of the exact method of solution cannot give solution. Therefore, we have to prefer the approximate method of solution. Approximate methods of solution are classified into two types. The first one is classical method and the second one is numerical method. Classical methods give solutions which are analytical in form. These classical methods are further classified into two types: variational method and weighted residual method. Now we shall see the variational method or variational approach. There are problems of engineering for which it is necessary to determine the extremum of a functional. Functional is a function of function. The first derivative of the functional is the first variance. When the first variance of the functional equals 0, which attains a stationary value. Once again I repeat, there are problems of engineering for which it is necessary to determine the extremum of a functional. The extremum may be maximum or minimum. What is functional? Functional is a function of function. The first derivative of the functional is the first variance. When the first variance equals 0, which attains a stationary value. Right? Now, the variational principle. We must be aware of this variational principle. How we state? If a certain law of mathematics or theoretical physics is expressed in terms of a line integral, the line integral achieves an extremum subject to some given conditions. Then such a physical law is said to be variational principle. The extremum may be maximum or minimum. The minimization of a functional defined for the given problem leads to formation of governing equation. Right? Now, we shall see an example here for extremum of a function. Extremum of a function. We have a simple function here, a function of one variable f of x. Visualize this picture. If you look at this, this is x-axis. Function f of x is taken as the ordinate. We have a smooth and continuous curve which is described by the function f of x. It is a function of single variable. Now, so this function has maximum at x equal to x1, which also has minimum at x equal to x2. Extremum may be maximum or minimum. To determine the maximum of the function, what is the condition? Or to determine minimum of the function, what is the condition? Now we shall see. So, for extremum of a function, the first derivative of the function should be equal to 0. Right? The first derivative derivative of the function is the first variance. For maximum or minimum of the function, the first derivative of the function equals to 0. So when you get the maximum of the function, see here, if the second derivative of the function is negative at x equal to say x star, then the extremum of the function is maximum. For maximum of the function, d square f of x by dx square must be negative. For minimum of the function, d square f of x by dx square should be positive. If the second derivative of the function is positive at x equal to say x star, then the value of the function is minimum at x equal to x star. That is what we see in this diagram. Say at x equal to x1, the first derivative of the function is 0 because slope of this function is 0. It is a smooth and continuous curve. And the same curve is having the slope here 0 at x equal to x2. Right? The second derivative of this function at x equal to x1, if you determine, you get negative. That is what we see here in this condition. At x equal to x2, the second derivative of this function, if you determine, you get positive. That is what you see here. So therefore, to determine maximum or minimum of a function, the first variance of the function should be equal to 0. So this is the condition. So remember. Right? In this example, as I said, fx is maximum at x equal to x1 and minimum at x equal to x2. Now, we take an example. So here in this example, there is an axially loaded bar with one end fixing. The cross section of this bar is uniform. E is the Young's modulus of this material. L is the length of the bar. This bar carries a distributed load, say Q per unit length, in axial direction. So therefore, I say it is an axially loaded bar. So what we do with this? So we formulate an equation, governing equation by variational approach. Right? To formulate the governing equation by variational approach, the total potential energy of this body we have to determine. The total potential energy phi is the sum of strain energy and the work potential. What is strain energy here? It is simply the internal potential energy due to internal forces. When the force Q is acting in the axial direction, internal forces are set up in this body. So therefore, the strain energy due to internal forces we determine. And what is work potential? The work potential is the external potential energy due to external forces. Q is the external force here. Right? So the total potential is determined here. Total potential is divided by pi. Pi equals to strain energy plus work potential. Now strain energy, how do you determine? Let us see. So here, to determine the strain energy of this body, the expression is half into half into sigma into epsilon into dV, integral of. This is the expression to determine the strain energy of this body. Half into integral of sigma into epsilon dV. Right? We also know that stress by strain equals to Young's modulus from Hooke's law. E is the Young's modulus. Okay? Now, this is epsilon. This is E. Epsilon. This is E. E is the Young's modulus. Now, in place of sigma, you can write E into epsilon. So therefore, the same expression we can write like this: half into integral of E into epsilon square dV. Okay? Right. Now, what is dV? It is the differential volume of the element. If you take an infinitesimal element of thickness dx, because the cross-section area is same, then dV you can write A into dx. Now, this integral form I take 1 by 2 into E, it is constant Young's modulus, therefore E comes out. A cross-section area of the bar, it is same throughout, therefore which also comes out, AE by 2 into integral of, right? So here x is varying from 0 to L. If I consider an axis x like this, x varies from 0 to L, therefore integral of as x varies from 0 to L. Now, epsilon square. If you consider a point here, if you consider a point here, under the action of this force, it can displace in the direction of loading. It can displace in the direction of loading like this. With displacement say U, therefore U is the displacement. Once you get the displacement, you can determine strain epsilon, and epsilon equals to du by dx. This is how I define. This is how I define. Epsilon equals to du by dx. Therefore, in place of epsilon square, I can write du by dx whole square into dx as it is comes. As it is, it comes here. So this is the expression for determining the strain energy. It is positive. Work potential is negative because it is the work done by external forces, hence minus of integral of as x varies from 0 to L. Now, so what is the force acting on this? Again, if you take an infinitesimal element of length dx, the force acting on the infinitesimal element is q into dx. Therefore, q into dx into the displacement u. Then you get the work done by the external forces. So this is the expression for the total potential energy of this axially loaded member. Right? Now, see here. When the total potential energy attains minimum value, a small change in displacement will not cause any change in the value of the total potential energy. To understand this statement, I take this example. So here, we can visualize a ball, spherical ball resting on a concave surface. If I give a small displacement to this, it comes back in a split second to its original position. So therefore, its potential energy is not changing. The reason is it has stable equilibrium. This example, if you see, a ball is resting on a convex surface. If I give a small displacement, it loses its position because it has unstable equilibrium. Right? This is the example for unstable equilibrium, and this is the example for stable equilibrium. Now this example can support this statement. The total potential energy attains the minimum value even if a small change in displacement of the body occurs. Right? So therefore, d by du of pi into delta u equals to 0. Here delta u represents non-zero displacement. That is the reason why d by du of pi equals to 0. This is equation number 2. Right? So we have the expression for pi. So here, this we have to differentiate with respect to u and equate to 0, then you get this expression. I hope so you are aware of differentiating an expression. Right? Okay. Next one. Now, what we do is, so you have to integrate this and you have to integrate this. To integrate, I use integration by parts. So when you integrate it by parts and simplify it, you get the expression like this. Okay? Now, on the left hand side of this equation, we have two terms. So this is the first term, AE into du by dx into delta u. And the second term is A into d square u by dx square plus q into delta into dx. Integral of as x varies from 0 to L and u varies from 0 to L. Okay. We have two expressions here. So this LHS equals to 0, right? When this quantity equals to 0, when this term equals to 0. So therefore I write separately. A into du by dx and delta u between the limits 0 and L equals to 0. This is one expression. And integral of A into d square u by dx square plus q into delta u dx equals to 0. This is another expression because delta u represents the non-zero displacement. So we write integral of as x varies from 0 to L A into d square u by dx square plus q into dx equal to 0. Okay. The first equation represents the boundary conditions and the second equation represents the governing equation for the axially loaded member. So what approach we have used to obtain these two? We have used the variational approach. Okay. The same example you can take and apply the mechanics of solids approach that we see here. The same example I take, same problem I take and I apply mechanics of solids approach. We have again an axially loaded bar with one end fixed, cross section is uniform, Q is the load intensity per unit length, E is the Young's modulus, L is the length of the member. I consider an infinitesimal element of thickness dx, right? Now, so what is the force acting on this face? It is A into sigma x. Sigma x is the stress acting in the direction of x-axis. Okay, right. On the right face, what is the stress acting? A into sigma x plus d by dx of A sigma x into dx. Okay. Now, considering the equilibrium of forces, if you write the governing equation, forces acting to the leftward I take negative, forces acting to the rightward I take positive. A into sigma x is the force acting leftward negative, and this is the force acting rightward. So therefore that is positive. a into sigma x plus d by dx of a sigma x into dx. And here q is acting rightward. Multiply this by length of this infinitesimal element, because q is the load intensity per unit length. That is the reason why the total load acting on this element q into dx, so plus q into dx. So from the equilibrium conditions, the sum of the forces equals to 0, right? If you simplify this, okay, if you simplify this, what happens? So minus a into sigma x plus a into sigma x get cancelled with each other, and what remains? D by dx of a sigma x into dx plus q dx equals to 0. This remains. Okay. Now, we know that stress by strain equals to Young's modulus. Therefore, the stress acting in the direction of x equals to Young's modulus into strain acting in the same direction. And the same expression you can also write as sigma x equal to E into what is epsilon x du by dx. I define the strain. Strain epsilon equals du by dx. U is the displacement in the direction of x-axis. So we have the expression for sigma x that I put here. So therefore, the simplified equation what you get from this will be written like this after substituting E into du by dx in place of sigma x. Hence we get d by dx of a into du by dx plus q equal to 0. We have assumed that the cross-section area of the body is same throughout. So therefore, A comes out. E is the Young's modulus of the material. It is same throughout. Sorry. It is same for the isotropic material. Right? So therefore, if you assume that E is also constant, which also comes out, the product A is constant. A into d square u by dx square plus q equal to 0. By variational approach also, we have obtained the same expression. So here, by solid mechanics approach also, we have obtained the same expression. Whereas in variational approach, we have obtained one more equation that represents the boundary conditions, that is the advantage of variational approach. That is what I have specified here. The mechanics of solids approach gives only the governing equation, whereas the variational approach gives both governing equation and the boundary conditions. Okay. Now we come to the summary, what we have learned in today's class. We have entered into the approximate methods. Approximate methods are classified into two categories: classical method and numerical method. The classical methods are classified into two types: variational method and weighted residual method. Right? Using variational method, we have formulated the governing equation along with the boundary conditions. So taking an axially loaded member as an example. The same axially loaded member we also took into consideration, and the governing differential equation was formulated using the mechanics of solids approach. So both approaches gave the same governing equation, whereas from the variational approach we have obtained additionally the boundary conditions of. Right? So we close learning. Thank you. Thank you.